Welcome to the demonstration of EE542 Lab 6. For this lab, we performed machine learning and deep learning for a banknote authentication dataset. Data was extracted from images which were taken from genuine and forged banknote specimens, and we downloaded the repository from the UCI ML repository, and the dataset had 1372 instances had 4 features: skewness, kurtosis, entropy, and variance, and one label, whether it was forged or genuine. We first performed some exploratory data analysis by making scatter plots of all the features pairwise and clearly differentiating the two classes, whether it's genuine or forged, as seen in the scatter plots. And then we had to select a suitable machine learning algorithm and then construct a training and testing set from the data set, and also build a model based on the chosen algorithm, logistic regression, and finally calculate the accuracy and F-scores. As you can see, these are the results obtained for the training set. We get a precision of almost 100% for both the classes and an F1 score of 99%. These are the results obtained for the testing set. As you can see, we get a precision of 100% for class 0 and an F1 score of 99%. And a precision of 98% for class 1 and an F1 score of 99%. We have also shown the confusion matrix for both the training and the testing set. The last step was deleting the instance and all the associated resources to avoid being overcharged. For part 2 of this experiment, we performed deep learning with AWS EC2 Deep Learning AMI. Then again, we divided the data into features and labels by splitting into training and testing set. After setting up the Amazon AWS EC2 instance, we imported the required libraries. We used TensorFlow to implement a neural network here. And then we also downloaded the dataset given to this EC2 instance and loaded it into a data frame. Again, we used the head function of the pandas data frame and also labeled the columns, as was done with AWS SageMaker. And we also plotted the scatter plots, which were the pairwise scatter plots of all the features in the dataset. For that, we used the pairplot function from the Seaborn library. Next, we set up the hyperparameters for the neural network. So we created a neural network with the input layer with 4 nodes, which correspond to the 4 features that we have, which was skewness, kurtosis, entropy, and variance. 2 hidden layers with 4 nodes each, and an output layer with 2 nodes, which corresponds to the 2 classes that we have. We then built the model for the neural network. So we used the softmax cross entropy as the cost function and an Adam optimizer. We then ran the neural network to calculate the training and testing accuracy. So it was trained by passing a batch of input and output data at each epoch, and using which the model basically updated its weights. We then plotted the graph of cost versus epoch, and then we were able to visualize the neural network, minimizing the cost function with every iteration. As you can see, for the training set, we have got a precision of 100% and also an F1 score of 100%. And also for the testing set, we have again got a precision and F1 score of 100%. This concludes the demonstration of EE542 Lab 6. Thanks for watching.